Okay. Hello, everybody. My name is Andrea Malchiodi, and I'm the current director of the Georgi Mathematical Research Center. So I would like to welcome you. And I will just say a few words, and I won't take much of your time, I promise. I'll say a few words about the Georgi Center. So it was founded about 20 years ago. With the goal of being like an occasion for the mathematical community in Pisa to meet, also with the colleagues from abroad. And so even though formally is a research laboratory of Scuola Normale Superiore, it's meant to be a sort of aggregation center. And the mathematical community in Pisa, apart from Scuola Normale Superiore, consists of the University of Pisa, of course, and also there is a small community at Scuola Superiore Sant'Anna. So since the founding of the center, the main activities are workshops, schools, intensive research periods, and we also organize visiting positions. So there are short-term visiting positions to perform research in pairs or in teams. And we also have 2 years postdoctoral positions. We also started recently a colloquium series. And basically, that's all I wanted to say. So I conclude just by thanking the organizers for bringing up this high quality event and also the staff of the center for their constant and precious support. Thank you.
Okay, thanks, Andrea, and good morning, everybody. So I'm very happy to introduce this workshop. So this is, as you know, this is the final workshop of our PRIN project, which is the project founded by the Italian Ministry of Education, University and Research, and it always changes names. So more or less, this is what it is. And so thanks to all the speakers and the participants to be here, and we are happy to hopefully share and the results of our project in the last 3-4 years, which actually the project has been, the deadline has been postponed due to COVID and so on. And so let me thank the organizers that have organized this event with me, Stefano, Roberto, and Carlangelo, who is not here yet, and all also the local coordinators of the project. The principal investigator was Carlangelo, but then the other local organizers, coordinators of the units were myself, Stefano Marmi, Marco Lenci, who is somewhere here, Roberto Artuso, and Olga Bernardi, who's not here yet. And I hope I'm forgetting someone. No, maybe not. And okay, so thanks to everybody. And so maybe it's time to start. Oh, yes, just a few announcements. So there will be a coffee break, which is served here, just on the table that you see there. Lunches will be also here by a catering. And so you're all invited to stay for lunches. And maybe I should also give a small advice that it's better not to use the chairs which are there. So please just try to only use the chairs which are already here for you. I think I'm not forgetting anything now. So thanks again to the center and all the staff for the organization, because they were very precious and helpful in the organization of this workshop. And then we will also thank the staff for the help, and they're also registering all the talks. So hopefully we will have the access to all the videos and of the talks. Okay, I think I'm not forgetting anyone now. So maybe we can start with the scientific program. And so the first speaker is Viviane Baladi, which I'm very happy to introduce. And I'm very happy that she is here again. She will talk about almost a parameter, almost sure invariant principle for the quadratic family.
Okay, so it's very nice to be back in Pisa. The talk is here. So I'm going to talk about an almost sure invariance principle in dynamical systems, but I'm going to spend a lot of time to give some motivation. So the title is Parameter Almost Sure Invariant Principle for the Quadratic Family. And if you don't understand what this parameter homogeneous invariance principle means, don't worry, it's normal. Nobody understands the first time, but I will try to explain. And it is joint work with Magnus Aspenberg and Thomas Persson. So it's an archive paper. And it's also a part of a long-term project that I have with Daniel Smania. So I will also mention a little bit my previous results with Daniel Smania and some other work with Daniel. So let me start with some motivation. This will take quite some time. So first of all, what do I mean by the quadratic family? I guess most of you know, but let me write it anyways, also because there are several different ways to parameterize it. And to fix ideas, I would like to use this way. So this is a map on the unit interval, okay? And A is a parameter. And so I would take A between 2 and 4. And actually, for technical reason, I don't want to take the full parabola. This would be for A equals 4. And the one point which plays a special role is a critical point, so the point where the derivative vanishes, which is 1/2, okay? And okay, I should have studied this before. So this one does not move, right? And this one moves. Okay, this is okay. So the one thing which will play an important role in this story is not only the critical point where the derivative vanishes. So this is the enemy, but also the iterates of the critical point. So C, and I should say C is equal to CA is equal to 1/2 for all the parameters, right? The critical point is the same for everybody. And then you can look at the forward orbit of the critical point, which sometimes I will also maybe denote by CAJ for J, 1, 2, etc. Okay, so this will play a special part. So now this is a conference about stochastics or ergodic properties. So we are interested in invariant measures. And actually, we're interested in absolutely continuous invariant measures. And what is interesting and now has been known for many decades is that there exists a positive Lebesgue measure set of parameters A such that TA admits a unique absolutely continuous invariant measure mu A. So by definition, this invariant measure has a density, which I call rho A. And one thing which you should keep in mind is that this rho A is in L1, but it's not bounded. And actually, it has singularities along these post-critical orbits. And the singularities of rho A, let me write it here. The singularities are of the type 1 over square root of x minus, well, I have a notation here, Caj. Okay. So this is a very famous result from the 70s or the 80s. And maybe I can just remind you about these good parameters for which we have such an invariant measure. And maybe I forgot to say, in addition, mu A is mixing, and we have exponential or decay of correlations for Hölder test functions. Okay, but what are these good parameters? So the most classical set maybe is a set of Kolle-Ekman parameters, which has a positive Lebesgue measure set. And those are parameters such that the derivative along the post-critical orbit. So you look at dTaj grows exponentially. Okay, those are the Cole-Ekman parameters. But then there are other parameters that I will talk about in this talk, and I think I need the other blackboard for this. So Cole-Ekman, so this has positive measure. And then there is a, let's say, Benedict-Carlson. And this would be the point such that CAJ is like exponentially something like this. I'm a little bit sloppy here, right? Because I don't have so much time. And then I can impose some stronger condition, which would be polynomial recurrence. So this would be CAJ minus C bigger than 1 over, let's say, J to the kappa for some kappa bigger than 1, and maybe all J bigger than some H0. And it's known that if kappa is strictly bigger than 1, the set of polynomial recurrent parameters has a full measure in the set of Cole-Ekman parameters. And then you can talk about Misiurewicz parameters. The condition is becoming stronger. Now you want the infimum of this to be strictly positive. So this one doesn't have a full Lebesgue measure anymore, but it has full Hausdorff measure in the set of Cole-Ekman parameters. And then you can impose some even stronger condition, which is Misiurewicz. So maybe I should say here full Lebesgue. This has full Hausdorff. And then Misiurewicz-Thurston would be that CAJ, there exists a J0 such that CAJ0 is periodic and let's say repulsive with a strictly positive Lyapunov exponent. And this one is very small, it's just a countable set. Okay, so there are all these good parameters. And now what is the question I want to discuss? The question is, you restrict to a set of good parameters, one of those, and you ask about the smoothness of this map, okay? So there was an old result of Tsuji, 1996. And Tsuji showed continuity. And I don't remember exactly which, so you can play a little bit with the sets. I forgot exactly which set he took, but one of the set of full Lebesgue measure. Full Lebesgue measure in Cole-Ekman, okay? So he showed continuity on a very large set of parameters. And then, of course, you could wonder, do you have more? You have Hölder continuity, you have differentiability. And the remark is that if this map, or let's say, I forgot to say something. One thing you can do is you can weaken, you have to make more precise what you mean by smoothness of this map. You have to say which topology you take in the image. And one standard possibility is to look actually at the smoothness in the sense of distribution. So you look at this map for psi in some class, for example, Hölder. But you could take also C infinity or some other class. And the remark I want to make is that if, and I call this map R of A, psi of A, And the remark is that if R of A is differentiable, this is not a very precise remark, but if this remark is differentiable, there is a candidate for its derivative. Let's say at a point A0. And I won't write the formula because it's a bit long to write, but let me just say that this candidate depends on the derivative of TA with respect to A, which is very easy to write. And it depends also on the derivative of rho A with respect to X, which is not so nice in our particular case, right? Because we have these non-integrable singularities when you take a derivative. So I won't write it, but let me just say that this is a value at Z equals 1 of a formal power series, which is called the susceptibility function. And now I see that I chose a bad name for the observable. I should call it phi, because the standard notation for the susceptibility function is psi Z. Okay, so I won't write it, but there is a candidate for the derivative which you obtain by taking the value at Z equals 1 of a formal power series. And the motivation, the main motivation for the all-motion invariant principle that I hope I will have the time to state before the end of my time is a following, the following two theorems, which I view as a paradox. So the first theorem is a theorem of Ruel. So he wrote one paper by himself, and then he extended slightly with Jiang. Both the papers appeared in 2005. And what did he show? So still on the blackboard, the definition. There's no T here. So they studied these Misiurewicz-Thurston parameters. And what do they show? They show that for any Misiurewicz-Thurston parameter, the function, this mysterious function psi of z, and for any reasonable function phi, extends meromorphically to the whole complex plane. And there is no pole at Z equals 1. So what this theorem says is that there is the candidate for the derivative is well defined. Okay, and it's not a completely trivial proof. I mean, you have to work, and it's kind of neat and okay. And now second theorem, which is in a paper I wrote with Benedicts and Schnellmann, also some time ago, 2015. So there are two statements. The first one is that for almost every CA parameter A0, there exists a set of polynomially recurrent parameters with containing A0 as a positive Lebesgue density points. So A0 belongs to delta A0 as a positive, as a Lebesgue density point, and which has the following properties, such that if you take a function which is 1/2 Hölder, this is my notation for 1/2 Hölder, then you look at this function R A of phi that we're interested in, then it is So I forgot the quantifiers. There exists a set delta 0, and there exists also a constant, such that up to a constant, this is almost 1/2 Hölder. There is a logarithmic factor, which we don't know if it's really there, but the proof gives it. And let me put here 5. Actually, we can get something a little bit better than 5, but let me put it. So it's almost 1/2 Hölder. Okay, and then the second part of this theorem, which is where I view a paradox, when you compare it to the theorem of Ruel just above, is that you also have lower bounds for this modulus of continuity, right? So you have an upper bound, which is almost 1/2 Hölder, but there is a second part in the theorem. There is a lower bound, but this lower bound, we only get it for very few parameters. More precisely, if you take a Misiorowicz parameter, Misiorowicz-Thurston parameter, so this is a countable set, right? So very few of them. So if this parameter is mixing, then there exists another set. Maybe I put a prime to show that they are really different. A set of Cole-Ekman parameters accumulating at A0 such that, and I forgot something, and there exists a special observable phi, such that if you take this special observable phi, which, as you can imagine, is doing strange things along the post-critical orbits, which is a periodic point, as you might remember. If you look at this special parameter phi, well, first of all, you have an upper bound, which is exactly 1/2 Hölder, so no more logarithm. And more interestingly, there is a lower bound, which is exactly, so phi, you can take it to infinity, and there is a constant, which is finite. Okay, so I hope I didn't forget anything. And so I view this as a paradox because we have a natural candidate for the derivative. And at the time when these results were proved, some people were very optimistic that the function Ra should be differentiable. But at the same time, you have this lower bound, which is clearly 1/2 Hölder. However, yes, exactly, yes, exactly, good point. This is only for A in delta prime. And I was going to say, to put a remark here, which is that this set delta prime, we don't know how big it is. In particular, we don't know if A0 is a Lebesgue density point of delta prime. So it could very well be that this set delta prime is actually very small, and then there would be no contradiction. So this we don't know. So if you don't know how to solve a problem, you go to an easier problem. And here there is a very natural, so I think I will remove the definition now. There is a very natural class of toy model maps, which are easier to study than the quadratic family, because the derivative is always bigger than 1, but which are still non-trivial. And I will now explain a little bit about this toy model. I'm just checking on my paper if I didn't forget. Yeah, let me just say one more thing, but I won't have much time to explain. So my belief is that actually the function Ra is not differentiable in any reasonable sense. And in order to understand this, with Daniel, we wrote a paper on fractional susceptibility functions, which appeared a couple of years ago in Communication and Mathematical Physics, but I won't talk about this, right? So let me now move to the toy model. So now, since the quadratic family is hard, we look at piecewise expanding maps instead. So it's maps which look like this. So the derivative now is everywhere bigger than, strictly bigger than 1. There is a point which maybe I could still see where the derivative is not defined. It's defined when you come from the left or from the right. It's not defined at C. So this is going to create problems. The post-critical orbit is again going to create problems, but it's not as bad because you don't have to worry about the derivative vanishes. And in particular, if you have such a family which satisfies reasonable smoothness in A, so it needs to be C2 or C3 in A, for example. Each map FA is piecewise C2, say, or let's be cautious and say C3. And so if you have a reasonably smooth such family, and you assume additionally something which is called transversality. So we assume transversality, which is a condition that we didn't need to assume for the quadratic family because it was like automatic. But if you take a family of piecewise expanding maps, you need to put this as an assumption. So what is transversality? What is transversality? Transversality is a fact that if you look at the post-critical, you look at the map. You look at the iterates of the map and you differentiate with respect to the parameter. It's the same thing as differentiating with respect to the phase space element. So let's be more precise. So this is bounded from above and from below for all J. So this is a toy model. You look at a one parameter family of such maps. And then for every A, you don't need a transversality for this, but for every A, there exists a unique absolutely continuous invariant measure. Maybe I still call it mu A, and it is exponential mixing. Okay, now it's for every A. You don't need to reduce a set of parameters to some strange counter set like in the quadratic family. And then you can ask again the question of the smoothness of the map sending A to mu A. Maybe I can point out that the density of mu A in this case is much nicer than in the case of the quadratic family. The density is bounded. Actually, it's a bounded variation. Okay. And you can ask again the question of how continuous, how smooth is a map A goes to phi d mu A, which again I will call RA of phi. I use the same notation as for the quadratic family. And so this problem is much better understood. So already in 1982, there was an upper bound by Keller, and he showed an upper bound A0, he showed Lipschitz corrected by logarithms. So this modulus of continuity. So he showed this upper bound actually for the L1 norm of the density. So not for the BV norm, but it's still a little bit better than taking a smooth test function. And then it took a long time before people tried to do more. And then in 2008, with Daniel Smania, we got a lower bound. So lower bound. But the lower bound was in the same spirit as the thing which is above here, in the sense that we could not get it for many parameters. So what we got is we got a sequence of parameters tending to A0. such that we have the lower bound Ra of phi minus R and some phi, which now I don't remember how smooth it was. Yes? So here, I think it's C1A. Yes, that was my notation. So the notation is C. Maybe, sorry, maybe sometimes I write like this and sometimes I write like this. Sorry. Yes, sorry. Yes. So if I look at A0, the image at A0 minus the image at AN, then I get this lower bound, which is exactly this one, up to a constant. Okay, and so again, it was not satisfactory. But the final solution of this toy model situation was given 10 years later. Wow. So in 2018, there was a paper by Amanda de Lima and Daniel Smania. And I've used this, I don't know if Daniel agrees, but I've used this as a final solution of the toy model situation. So what did they show? So let me write the conclusion of the corollary of their main theorem. And let me remind you that we always assume that we have transversality, right? So we assume that we transversality. What they show is that for any, so you fix some A0, and then for any set delta, no, I don't need to fix A0, sorry. I don't need to fix A0. For any set delta of positive Lebesgue measure, the map A to R A of phi is not Lipschitz. And let's say for every generic phi, for generic phi, is not Lipschitz on delta. Okay. So I will be a little bit more precise, but I think that's a fair way to state the corollary. And so in particular, this shows that you cannot get a linear response, or you cannot get differentiability of the function Ra in any reasonable sense, okay, on a set of positive Lebesgue measure. And generic phi, basically, if I remember correctly, it means that it's smooth enough and that the variance, which I'm going to define in a minute, is non-zero, okay? Okay, and so I will say just a little bit more about, yes? Yes. So you change the slope. Yes, that's a good question. Yes. If you take the map or you just change the slope, then it satisfies the transversality condition. Thank you. Yes. Okay, so I will not, of course, give the proof of this theorem, but I will explain now why we get to this almost sure invariance principle, because you might be frustrated and wondering. So the proof of this theorem, the proof of the theorem which I just stated, the proof uses a so-called functional central limit theorem for the post-critical orbit. So maybe I write it explicitly. Okay. And if you don't know what is a functional theorem, then it's a consequence of the almost sure invariance principle for this. Okay. And fortunately for them, for Amanda and Daniel, this almost show invariance principle in this setting was proved by Daniel Schnellmann in 2015. Okay, so this is a key to show this. What they do actually is they prove some kind of central limit, non-standard central limit theorem for this function, which are RA of phi. And they deduce from this that it's not possible because they have this logarithm in the denominator. They don't have just epsilon, they have log epsilon epsilon, and so you cannot have a Lipschitz function. Okay, so now I will look at the time. So how much time do I have? Because we started a little bit late, no? So half an hour. Okay, good. So so now I will just, I know that a lot of people in this audience are very familiar with probability theory and almost sure invariance principle, but I will just remind what I mean by almost sure invariance principle for those who are not familiar. So so first in words. So in words, almost sure invariance principle is an almost sure approximation by or with a sum of IID variables, Gaussian, of course, Gaussian random variables, which is the same thing as sum of IID Gaussian random variables, same thing as Brownian motion at integer times. Okay, this is just like in words, what is almost sure invariance principle. So let me be a little bit more precise. So definition, this is a general definition. We have a probability space, and we have a sequence of random variable. Let's say revalued. Satisfies the almost sure invariance principle with error parameter, what is the word? Error exponent, with exponent gamma. So it cannot be better than 1/2 if now there's some probabilistic hocus pocus, which a lot of people in this room are much more familiar with. You have to change a space because you don't have Brownian motion on all spaces. So you have, this is a bit annoying, but I mean, I just want to state it precisely. If there exists another probability space, which could be the same actually, but in principle, it can be different. So if there exists another probability space supporting 1D centered 1D Brownian motion, which I call W, and a sequence of measurable random variables on this, sorry, it's W here, random variables on this potentially different space, such that the two following properties hold. First of all, you didn't change anything. So the psi and the etas have the same distribution. Okay, so you have sequences of families who say that they have same distribution. It means that the joint distribution for any finite subset are the same. So the probabilities that you have some inequalities satisfied. So this was just the hocus pocus. And now the interesting part is that if you look, so now you have this new family, which is the same as before for all practical purposes. If you look at the new family, so you sum up to n, and you look at the Brownian motion at the integer time n, then it's the same thing, modulo an error which is not worse than gamma. almost surely. Okay. So this is just to remind those of you who are not familiar with the homogeneous principle what it means. And now I want to say just a few words before I state our theorem about what I mean by homogeneous invariant principle in the setting of the application to get the result of the lemma and the Smania. And so I notice when I talk about this to people informally, it's always a bit confusing because they tell me, oh, but Melbourne and Nicol already proved the homogeneous invariance principle 20 years ago. And that's true, but they prove a different invariant principle. So, so let me just make a very quick historical parenthesis. So the homogeneous invariance principle was proved in several settings, and in particular, indeed, Melbourne and Nicol. There are two L's, no. 2005. What did they show? They show the following result. So now we're back to the quadratic family. Okay. So they looked at the quadratic family. They took the fixed parameter. They fix a parameter A0, which is called Ekman. They take as a probability space the whole interval, so 0, 1, or maybe you know, the first and second images of a critical point, but let's not worry about this. They take M star, I hope it's the same notation, yes, M star omega star. They take M star to be mu A0, and F star to be the Borel sigma algebra. And what do they show? What do they show? They show that if you take the random variable from omega star, so 0, 1 to R, and you define psi j of x to be T A0 j of x, they show that this satisfies an homogeneous invariance principle. So this is another homogeneous invariance principle in the phase space. Okay, so the probability space here and the measure there are in the phase space, which is a great result, but that's not what we need. Okay, what we need, so this is in a phase space. What we need, or what Amanda and Daniel needed, was the theorem of Schnellmann, which I alluded to on the previous blackboard, which says the following thing. It says you take omega star. So sorry, I shouldn't have said back to the quadratic family because now I'm back in the toy model. So sorry. Back to the toy model. So now the result of Schnellmann was for the piecewise expanding maps. So you take omega star to be the set of parameters, which is an interval, which I didn't specify when I was talking about, it's not a counter set, it's an interval of parameters. And what measure do we take? Well, we don't have an invariant measure anymore, so let's take the measure which we like, which is Lebesgue measure. And F star to be Borel sigma algebra. And what did he show? He showed that if phi is Holder, for any phi Holder, such that, and I will tell you in a moment what this is. So we take any point in this interval, we take a function which is Holder, and we need to assume that its variance, which I will define in a moment, is non-zero. We have that psi j of A, which is phi A, and I will tell you what is phi A in a moment, phi A of Taj of C satisfies an almost sure invariance principle, and let be a bit more precise for any gamma, for any error exponent bigger than 2/5. You cannot go all the way to 1/3, which would be the IID case. At least his proof doesn't give it, and it looks like it's really a serious obstruction. So let me tell you what is sigma A and phi A, which are also used to state our new result. So first, let me read what I wrote to check I didn't forget anything. So you take this a set of parameters, Lebesgue measure, and the statement is for any Hölder function, for any parameter in this interval, this is an interval, right? For any A0 in this interval, if this variance is non-zero, then the sequence of random variables on this interval of parameters for this measure, which is Lebesgue, satisfies the almost sure invariance principle for any parameter which is strictly bigger than 2/5. Okay, so now let me introduce this notation of sigma A and so what is the point of this sigma A and phi A? You just want zero average and variance 1, right? You need to normalize. So how do you do that? You define sigma A of phi squared to be, and the expressions which I'm going to write are well defined because we know that I think I mentioned it before, we know that we have exponential mixing okay, now I'm not sure what I wrote is correct. Yes, I square and then I take the average, yes. And then I have this sum plus j bigger than 1. And then I have this, maybe I should have introduced a notation for this normalization. And then the same thing, but composed with the dynamics. Well, since we are in the, I should put F, I guess, it's piecewise expanding. Okay. So this is like a correlation. This is, I don't know if it's possible to read, composed with FHJ. This is a correlation, decorrelation. This is summable. And this is, so this is a well-defined number, which is non-negative. It's an exercise to show it's non-negative. And the assumption is that this number is strictly positive. Okay. And now what is phi A? Phi A is, well, first you remove the average, which what we did in the previous formula. And then we divide by the variance. Okay, sigma A of phi. Okay, this is a result of Daniel Schnellmann. Unfortunately, I don't have the time to talk about the proof because I'm sure there are experts in this room who know everything about martingale approximations, Koch-Rod representation, etc., etc., etc. So I won't talk about the proof, but it's inspired by a famous book of Philip and Stout, the Philip and Stout argument. Okay, so now what is a new theorem? So I think I will have the time to state it at least before the end of my time. And I hope that now you are, you will understand why it's an interesting theorem in view of trying to clarify this paradox for the quadratic family. And so now it's last time we changed topics. Now it's for the quadratic family again. So this is our new result. So with Aspenberg and Persson. Well, I guess you have guessed what the result is, modulo a few details. So first question is, well, we cannot have all parameters in interval, so we will need to have some counter set of good parameters. And so what could we do? Well, first of all, we need to start with a Misurevich point. So let me remind you that this is a set of full house of measure. And these are the sets which avoid, whose post-critical orbits avoid a neighborhood of the critical point. And I cheated a bit before. I told you transversality is automatic for the quadratic family. Actually, it's automatic, but you still have to check that it's satisfied. So, okay, there is a transversal. Oh, sorry, not exist. For any A star, which is transversal and Misohevich, and there are such points, they exist. And mixing. To get mixing, you just need to be close enough to the value 4. That's not a strong assumption. There exists, and this is our omega star now, except that omega star now is a counter set, but it is a positive Lebesgue measure counter set, and it contains A star as a Lebesgue density point. Such that the following holds. For any Hölder function with sigma A star of phi non-zero, and sigma A star of phi is defined in the same way as before, except that you have to replace big F by big T, right? The sequence, the random variables, psi j of A, which you obtain by the same formula as before. Here it was actually F. Now it's really T. And here I suppose I should have started with C1. C1A. And this is for A in, so maybe you have to replace the counter set by the counter set intersected with a neighborhood of A star. So you take all the points in a counter set which are close enough to A star, and this neighborhood depends only on, you want this property to be still satisfied for A in the neighborhood. And they satisfy the almost show invariance principle for the same range of error exponents as in the previous theorem. So for all gamma bigger than 2/5. Okay. And I think I still have a few minutes actually. Great. So let me read what I wrote so to check it's correct. So we start with a transverse Misohevich and mixing parameters. So there are a lot of such parameters. We find a counter set which contains A star as a Lebesgue density point, such that if you take a Hölder function which does not have zero variance, then there will be a neighborhood in this counter set, a neighborhood of A star in this counter set, such that, I forgot to say, which measure do we put? We put the Lebesgue measure, normalized Lebesgue. When I stated Schnellmann's result, I think I forgot to say that we normalize Lebesgue, right? It's normalized. We want a probability measure. So we take normalized Lebesgue measure, and we take this sequence of random variables, and they satisfy the almost show invariance principle for the same error exponents given by the result of Schnellmann. And I want to make a few historical comments, and then I say just very quickly a few words about the proof. So, as I mentioned before, this almost show invariance principle implies what is called the functional central limit theorem. It also implies a law of the iterated logarithm. Okay. And of course, it's stronger than the law of large numbers. So let me make some remarks. The law of large number, that's an old result. I don't know, I forgot the year, but it's Avila Moreira. Does anybody know the year here? But it's kind of oldish, like more than 10 years ago. Like 2000, 2003 or 2005. I don't know which paper. So it's old paper. So they show the law of large number. What more precisely, for Lebesgue, almost every Cauchy-Ekman parameter is 0. For all continuous test functions, if you take the Birkhoff averages along the post-critical orbit, they converge to the average with respect to the absolutely continuous invariant measure. So this was already known for a long time ago. And then there's this other result, which is a law. This is law of large numbers. This is law of the iterated logarithm. Law of the iterated logarithm. So this is actually a work in progress of Gao and Shen. So Shen is Wei Xiao Shen, and Gao is one of his former students. I forgot which one. He has at least 2 students called Gao, Bing Gao, I think. And this has been in progress for many, many years. So I don't know why they don't write it up. But so let me give you the statement, because it's not really implied. Although our result is stronger because it's almost showing invariance principle, and they only get the law of the iterated logarithm. They have a slightly different statement because they get it for Lebesgue almost every Cauchy-Ekman parameter. So for Lebesgue, almost every mixing transversal Cauchy-Ekman parameter, let me call it A0. I could also call it A star. For any Hölder phi, there is a dichotomy, either sigma A, let me call it just A, sigma A. Either sigma A of phi is 0, or we have the law of the iterated logarithm. And in case you don't remember what it is, I'm going to write it up for you. So you divide by 2, there's a factor to 2n log n, which is our iterated logarithm. And you make the Birkhoff sum. And you take just take the normalized guy like this, Taj of C minus the average. You take the limit. And this converges to this variance. Okay, so just to mention that there is another work, and they use a completely different method. And I guess I have to stop more or less now, but let me just say a few more words. They use in particular a completely different parameter exclusion technique. And the reason, yeah, I didn't tell you the whole truth. So we find this positive Lebesgue measure set, which contains our anchor, a starting point A star. And how do we obtain it? We obtain it by doing some Benedict-Carlson type exclusion, except that instead of excluding parameters by removing those which come exponentially too close to the critical point, we remove those which come polynomially too close. And this is because we want to apply directly some results of the previous paper that I wrote with Benedict and Schnellmann. And so this set has positive Lebesgue measure, but it's not very big, in the sense that if you look at its complement, then we cannot show that the measure of an interval in the complement decays like exponential epsilon to the power beta for any beta smaller, strictly smaller than 2. So we cannot show that. And whereas since they use a completely different method, they can get much more parameters. So we show a stronger result on less parameters, and they show a weaker result on more parameters. And yes? You're probably right, but I don't know actually. Maybe they actually normally it's a lim. No, you're right. It's lim sup. Sorry. Thank you. I knew there were experts in the room. Thank you. Yes, it's their theorem. It's not mine. So yeah. And just the last word. So of course, as I explained in the beginning, this is just like a stepping stone to understand the quadratic family. And because of the pandemic, we have a project with Daniel. It was a bit stalled during the pandemic. But the past 2 weeks, Daniel was in Zurich, and we have some. Well, we are starting to remember what we did 5 years ago, and we have some hope that eventually we can use this this result. And I will stop now. Thank you for your patience.
Okay, so then our next speaker is Alberto Abbondandolo, who is back again in Pisa after some years. And so he will talk about symplectic capacities of domains close to the ball and quasi-invariant contact forms.
Okay, so thank you very much. Thank you very much for the invitation. For me, yeah, it's really a pleasure to be back in Pisa. Okay, I would like to talk about something concerning, say, the broad topic is symplectic rigidity. So the setting is that we are in R2n, a typical phase space of a Hamiltonian system with a standard symplectic form, dpj, dqj. And as you know, symplectomorphisms, so we're interested in understanding a bit the nature of symplectomorphisms. So let's say diffeomorphism between open subsets of R2n, which preserve the symplectic form. So the natural transformation of classical mechanics. And as many of you, I'm sure, know, a breakthrough in this understanding of symplectomorphisms was Gromov non-squeezing theorem from 1985. Gromov non-squeezing theorem says that you cannot squeeze a big ball into a thin cylinder with a symplectomorphism. In other words, if R is bigger than S, there exists no symplectic embedding from the ball of radius R. So symplectic embedding I will just denote by this, with an embedding with an S above this. So it means a symplectomorphism which maps the ball. This is the ball of radius R, and we would like to embed it into a cylinder of radius S. This cylinder of radius S is just a disk of radius S, so two-dimensional, in, say, in the variable P1, Q1, cross everything else. Okay, so the ball has finite volume, the cylinder has infinite volume, but nevertheless, with a symplectomorphism, you cannot squeeze. Yeah, which means that there should be invariants which go beyond volume for symplectomorphism. And then in the early 90s, motivated by this result, Eckel and Hofer introduced the notion of symplectic capacity, which was a way of so a measurement going beyond volume, which should be preserved by symplectomorphism. So a symplectic capacity, they define it axiomatically in this way. So a symplectic capacity. So this is in our setting, let's say in R2n, it's a map C from, let's say, open subsets over 2n to non-negative numbers, possibly plus infinity. We should satisfy some axioms. Here are the axioms. The first axiom is that this symplectic capacity should be monotone with respect to symplectic inclusions. So if A embeds symplectically into a set B, then C of A should be less or equal than C of B. So in particular, if two sets are symplectomorphic, if there is really a diffeomorphism, which is a symplectomorphism between them, then they have the same capacity. Then it should scale as an area. So C of R times A should be R squared C of A, where we are positive. So not as a volume, it should scale really as an area. And of course, if you just ask this, say volume to the power 1 over n would still be fine. But the other important thing is the normalization. The capacity of the ball of radius 1 should be the same as the capacity of the cylinder based on a disk of radius 1. And let's say this is pi. This is the usual normalization. Okay, this is a Ecklen-Hofer definition of a symplectic capacity. And the important observation is, of course, if you have a symplectic capacity, then the non-squeezing theorem trivially holds, right? Because the ball of radius r has capacity r squared pi. The cylinder of radius s has capacity s squared pi. So you can, if you can embed, you cannot embed if r is greater than s. Okay, and actually Ecklen-Hofer introduced a symplectic capacity. It was defined using periodic orbits or Hamiltonian systems, and by this they gave a new proof of Gromov theorem. Conversely, Gromov theorem gives us, in some sense, somehow trivial, or let's say extremal symplectic capacity. Namely, you can look at, I call it CB of A. You can look at the biggest ball that you can embed symplectically into the open set A. So you take the supremum of pi r squared such that there exists a symplectic embedding of the ball of radius r into A. Okay. By Gromov non-squeezing theorem, this satisfies all the axioms of a capacity. And the other one is, instead of embedding balls, you can embed your set into a cylinder. So I'll call it CZ of A. This is the infimum of pi r squared such that there exists a symplectic embedding of the cylinder into A. Okay, both these are symplectic capacity. In some sense, they are non-computable symplectic capacities because they are defined through embeddings, and embeddings is what we would like to use symplectic capacity for. But they're important because any symplectic capacity will be squeezed between these two by definition, basically. Yes, thanks. We want to embed the set into the cylinder. Yeah, thanks. Pi, if it's called, yes, either pi square or ZR. Thank you very much. Okay, these are symplectic capacities. And yeah, these axioms, unfortunately, do not determine symplectic capacities uniquely. There are examples of nice star-shaped sets for which, for instance, CB and CZ are different. By the way, this one is called in the literature Gromov width. This other one is called cylindrical symplectic capacity. But already in the early 90s, people started wondering. There was this question, which is still open after, more than 30 years. Do all symplectic capacities coincide on convex domains? I always mean here bounded. I won't write it. I always domains. Let's say today domains are bounded. Now, if you go beyond convex domain, you can find nice star-shaped domains for which, symplectic capacity. There are different symplectic capacities which do not coincide. However, for convex domain, an open question is whether all symplectic capacities coincide. And there is some, there was already in the 90s evidence for this, for a positive answer to this conjecture. The evidence was mainly that all the, or not all, but say for many of the computable symplectic capacity. So to define symplectic capacity, you can use either periodic orbits or pseudomorphic curves or Lagrangian manifold, or you can mix this ingredient and then you can create with tools from symplectic geometry, you can build many symplectic capacity. And for many symplectic capacities, it was shown, so for many C, it was shown that the symplectic capacity, if K is convex, this is convex, then the symplectic capacity is, in some sense, it's a dynamical invariant. I call it systole. This is the systole of K. So let me clarify what is this systole of K. So K, let's say here in this case, K is convex with smooth boundary. It's not really essential, but by the way, these symplectic capacities are by definition continuous with respect to the Hausdorff distance because of these inclusion properties. So if you understand then on convex domains with smooth boundary, you have understood everything also in the non-smooth case. And then in this case, the systole is just the, so this is the minimal action of a closed characteristic on the boundary. So maybe let me explain what I mean by this. That's K, yeah, thanks. Yeah, convex sets depends on the language. Now I moved to Germany, and so it became K. Okay. So we have our, so the boundary now is a nice hypersurface in our R2n. And on every hypersurface in R2n, we have the so-called characteristic foliation. Now, this is just one way of defining it is you take the symplectic form. Okay, this is non-degenerate, but once you restrict it to the tangent of a hyperspace of a hypersurface, it's to form on an odd dimensional space. If you have a kernel, the kernel will be one dimensional, and this is the direction. This is a line bundle which whose integral lines are the characteristics. Okay, or equivalently, you take any Hamiltonian function with this surface as energy level, and these are the orbits of this Hamiltonian system. Or still equivalently, you think of, this will be useful. You think of R2n as Cn. Take your surface, take the normal, rotate it by I. Here we have the rotation, multiplication by I. And this is a vector field which will generate the characteristic foliation. Okay, so this is the characteristic foliation. And yeah, on the boundary of a convex set, one always have closed curve for this characteristic. So the characteristic foliation is complicated, it's a Hamiltonian system, and but they always have periodic orbits, so there are closed characteristics. And by action, I mean action. So we either integrate omega on a disk bounded by this curve, or we integrate a primitive of omega on this curve. Okay. And okay, so for many capacity, it was shown that the capacity actually, when restricted, so in general, it's not true. If you take on star-shaped set, it's a different thing. But for convex set, it's this. It's the smallest action of a closed characteristics. Okay, but this is known for many C, but it's not known. For instance, it's not known for CB, and it's not known for CZ, for these extremal ones. So it's just evidence towards positive answer to these questions. Other questions before I start writing on the other blackboard? Okay, then why is this question interesting? This question grew in interest in the early 2000s. So in exactly year 2000, Claude Viterbo stated a conjecture. So it's an inequality for isovolume inequality for symplectic capacities. So again, if K is our convex domain, bounded as always, Viterbo's conjecture states that the capacity of K to the power n should be less or equal than n factorial times the volume, with the quality if and only if K is symplectomorphic to a ball. Okay, in other words, if you fix the volume and you try to maximize the symplectic capacity, the maximum is achieved precisely at the ball, and then of course at all other domains which are symplectomorphic to a ball. Okay, this again, it's an open conjecture, but it is trivially implied by a positive answer to this question, because the smallest symplectic capacity, so CB, satisfies this inequality. Yeah, basically trivially, because if you can embed this ball, then the volume will be bigger than the volume of the ball. So the Gromov width trivially satisfies this inequality. So if all symplectic capacities for convex sets are the same, they all satisfy this inequality. And yeah, this conjecture by Viterbo is open. In general, the best known results, so Viterbo himself proved that this is true up to a constant here depending on the dimension. And this was refined in, I think, 2008 by Vitaly Milman, Yaron Ostrovero, and Shirya Stanavidan, who showed that so the inequality in some sense is asymptotically true. So it's true up to a constant which is independent on the dimension. Okay, but the question is really the sharp constant is the open question. Okay, so this is one motivation. And another motivation was the fact that Viterbo's conjecture, so Viterbo implies Mahler. So there is a much older conjecture, this time in convex geometry. It's known as the Mahler conjecture. This states that if K is in Rn, and it's our convex body, let's say it's symmetric with respect to the origin. K is minus K. So this time we are in Rn. But then what we do is we look at the volume of K times the volume of the polar set of K. Now, the polar set of K is the polar in the sense of convex geometry, or in other words, K is a symmetric convex body, so it's the unit ball of a norm, and the polar set is the unit ball of the dual norm. Okay, and if you look at the product of these two volumes, this is a linear invariant. If you apply a linear transformation to K, you will apply the inverse of the adjoint of it to K polar, so the product of the volume stays the same. So it makes sense. So for instance, you can dilate K and then you will shrink K polar, the volume stays. So it makes sense to try to maximize and minimize this quantity. And maximizers are known. So it's known that this is maximized by the ball and therefore by all ellipsoids. This is known as Blaschke-Santalo inequality. The open question, this is Mahler conjecture, is minimizers. So the conjecture is that this should be greater or equal than 4 to the n factorial, which is what you get when K is a cube. But unfortunately, not only cube. There are many sets for which you get this same value. At least all class of convex bodies called known as Hanner polytopes. They all have this Mahler volume. This is called Mahler volume. The conjecture is that they are the minimizers of Mahler volume. And again, this is open. So it's open in arbitrary dimension. The first bounds from below were proved by Bourgain. And the best bounds known so far are bounds found by Kuperberg, which are, here there is a constant, but quite close to 1. And the conjecture is known to be true in dimension 2. Mahler himself, here we are in the 40s. So 8 years ago, Mahler himself proved his conjecture for in dimension 2. And 5 or 6 years ago, Irie and Shibata proved it in dimension 3. Okay. And again, Shiri Arstanabidan, Yaron Ostrover, and Roman Karasev proved that if Viterbo's conjecture is true, then also from Viterbo you can deduce Mahler. Okay, so in some sense, the hierarchy here is there is this conjecture. If all symplectic capacities coincide, then Viterbo's conjecture is true, and then also Mahler conjecture is true. Okay, so we are going, say, time in the future. We make conjecture in some sense they are more and more difficult. But of course, the hope is that even if then these questions are in some sense more difficult than Mahler original question, which is still unsolved, the hope is, as always, that sometimes seeing things in a broader settings make you find proofs where using methods. Yeah, well, that's exactly, the thing is that if you take a cube cross its polar, the interior is symplectomorphic to a ball. For the cube, this is known actually, and it's still unclear. So conjecturally, then this is true for all Hanner polytopes. That if you take Hanner polytopes time its dual, time its polar, the product in R2n now is symplectomorphic to a ball. Yeah. This is a good observation because here of course the ball instead is not the minimizer, and actually the ball also because here it doesn't minimize, and the thing is that ball cross ball, this is a ball in a Lagrangian subspace. The ball in the Lagrangian subspace times the other ball. This is not the ball, is not symplectomorphic to a ball, but the cube is. Yes. Actually, this leads to very interesting questions. When you have, in particular, polytopes. You have polytopes in R2n, in Rn times the polar. Which polytopes give you sets which are symplectomorphic to balls? And this goes quickly in the direction of understanding integrable Hamiltonian systems, because the ball is very integrable. Okay, so these are these questions. Yeah. In a sense, to do the whole thing, you would like to get Viterbo with the optimal characterization of the thing, and then to prove also that this is it satisfies precisely at Hanner polytopes, and these are the only convex sets such that K cross their polar is symplectomorphic to a ball. Let's say in the optimal world, if there are no surprises, this would be the thing, but well, one never knows. In this thing, there are often surprises. Okay, other questions? Okay, then let's go to what we can prove. This is a theorem we proved recently together with Gabriele Benedetti and Oliver Ettmeyer. So Gabriele Benedetti is in Amsterdam, Oliver Ettmeyer in Berkeley. What we proved is all symplectic capacities coincide for convex sets which are sufficiently close to the ball. For K sufficiently, and close here means C3 closed. So again, we're looking only at convex sets with smooth boundaries, and then it makes sense. You can imagine what it means that our convex set is C3 closed to the ball. So there is a neighborhood, a C3 neighborhood of the ball, where all symplectic capacities coincide. So it's, if you want, it's the perturbative case of this question. So perturbatively, the answer is yes. Okay, and yes. Well, one consequence is that Viterbo then holds true for those, but actually, yeah, now I'll tell you a bit the story about this theorem. That Viterbo holds true in this set. We had proven it before. And unfortunately, about Mahler, you don't get much. Actually, about Mahler, also because for Mahler, it's already known that at least near the cube, but in this case, near means Hausdorff near, so C0 instead of C3, the Mahler conjecture holds. If you take something which is Hausdorff close to a cube, then you have Mahler inequality. So about Mahler, we don't get anything anything new. About Viterbo, okay, we found again something that we already had proven a couple of years before. Okay, and yeah, a bit history of this theorem. This, in sentence, is the conclusion of a long project. Let's say in dimension 4, this was about 6 years ago, with Barney Braham, Umberto Rigniewicz, and Pedro Salomao. We proved that the Viterbo conjecture is true C3 close to the ball, but in dimension 4. And there we were using the fact that we're in dimension 4, we go to the boundary. So we have a dynamical system in dimension 3. And there we could use global surface of section for this flow, reduce things to the dynamics of disk maps, basically. And then it was a result about fixed points, finding fixed points of disk maps based on the clubbing, with bounds with respect to the clubbing variant of these maps. But it was also methods which were only low dimensional. And then with Gabriele, we proved this 2 years ago that the Viterbo conjecture holds true near the ball, instead using normal forms, something which will appear also later in my talk. And Oliver, in the meanwhile, had used our method of global surface of section in dimension 3 to prove this result in dimension 4. So dimension 4 is due to him. And then we joined energies, and we proved that in every dimension we get a positive answer to the question of all coincidence of all capacities. Okay, yeah, I have 20 minutes. Maybe I can tell you something about the ideas involved in this proof. So here, so we want to prove. So the inequality is still there. We want to prove two things. We want to prove it suffices to prove that this outer capacity, the cylindrical capacity, is the same as the systole if we are C3 close to the ball. And this is actually easy. Let me just wave hands and tell you why. This way, actually, yeah, we had noticed it much before. What is the situation? We start with the ball. Okay, the ball, what is the characteristic foliation on the ball? No, you take the normal, you rotate by I. So the characteristic foliation is nothing else it's the Hopf vibration. It's you take this ball in Cn, you intersect it with one-dimensional complex spaces. So there are planes that are complex dimension 1, and you obtain a great circle, and this is an orbit of our system. Okay, it's just that. So all characteristics are closed. Okay, and now you perturb this a bit. You will destroy many of these periodic orbits, but some periodic orbits will survive. And actually, they will survive, and they will be very close to the original ones. So which means that you have now the systole, so the closed orbit with minimal action, will be close to a great circle in a complex line. And then the thing is that with a symplectomorphism, you can bring it back to be really a nice circle in the complex line. Just because symplectomorphism act transitively on closed curves, you just need to know that the action is the same, and then you can bring a closed curve to another one. This is not a problem. And actually, if these things were close, you can check that also the symplectomorphism will be sufficiently close to the identity. And in particular, it will preserve the convexity, because our sets are uniformly convex. They have really positive curvature. So you do it, you bring your systole in this plane, but by preserving convexity, by a symplectomorphism. And now you have already the cylinder where it sits in. So this is, you have just to be careful to build this symplectomorphism to be sure that C3 is what you need. You use, generating functions, but it's no big deal. Okay, so the true thing is to prove that the Gromov width is the systole. Okay, this is the delicate part of the proof. And so here the idea is we want to do the following. So we have our K is close to the ball. What we want to find is to find a K prime symplectomorphic to K. So we want to modify K by a symplectomorphism in such a way that K prime now has the following property. I'll do it with a picture. This is my K prime. Need not be convex anymore. This is not really relevant. But K prime, if I look at the biggest ball inside it, again, center at the origin. We still keep this center at the origin. I look at the biggest ball, which I can put in here. What I would like, so this will touch the boundary of K prime somewhere. What I would like is that in this touching set, there is at least one full orbit of the flow of the ball. So the condition is that the boundary of K prime intersected with the boundary of this maximal ball, let's call this VR, contains a full, so let's say V intersected boundary of VR, where V is a complex line. V is a linear subspace of the, this is a complex line. No, so we have this full thing. No, because if we have this, so these two sets are tangent. So if the sets are tangent, then they're, if you want, the Hamiltonian vector fields, there are parallel. So this means that this full orbit, which is an orbit, it's a closed orbit for the ball, will be also a closed orbit here for the set. And so the systole, maybe it's even smaller, but then we would get that the systole of K, which is the same as the systole of K prime, is less or equal than this, than the systole of this ball. But the systole here is monotone, so this will be less or equal than the systole. So this is the same of the capacity of the ball, but the capacity of the ball is less or equal than the capacity of K prime, which is the capacity of C. So eventually, systole and capacity have to coincide. Okay, so this is what one would like to get. In some sense, we are not assuming any S1 invariance. We cannot say that the set is S1 invariant, but we would like to bring it in some situation in which it's almost, in some sense, it's almost invariant, or at least it has a big invariant part. Okay, in order to achieve this, here I need to introduce a bit of language. In some sense, I need to introduce a bit the language of Reb dynamics, because this is eventually, it's a result about, it's a normal form for contact forms. This is what it boils to eventually. Or if you want, it's a normal form for Reb vector fields. Okay, so for now, let's forget for the next 5 minutes about the problem and just primer on these Reb dynamics. So Reb dynamics. Okay, what is the picture here? We have a manifold, let's say, of dimension 2n minus 1, or dimensional, closed manifold. And on this manifold, we have a contact form. So alpha is a contact form. Contact form means just that alpha, it's a one form. And alpha wedge the alpha to the top power, in this case, n minus 1, is everywhere non-zero. So it's a volume form here. Okay, this is the contact form. Actually, its kernel is called the contact structure. And of course, any other contact form having the same kernel will be just a function multiplied by this one. But then to a contact form, we can associate a vector field. This is the Reb vector field, R alpha, which depends instead really on the contact form. R alpha is defined by saying that if I take the differential of alpha, this is as non-degenerate as it can be on an odd dimensional thing. So it will have a kernel. And we want the Reb vector field to be in the kernel. So if we contract the alpha in this direction, we want to be 0. This fixes the direction of the Reb vector field. And the other condition, normalization, we want alpha on the Reb vector field to be 1. Okay, so Reb vector fields in dynamics are often also called contact vector field. But yeah, terminology is maybe not optimal, because if you think contact vector field as vector fields whose flow preserve psi, they are a bit more general than those. They could have zeros, for instance. Okay, so I'll call them Reb. These are Reb vector fields. And yeah, every contact form determines a vector field. And conversely, if I have the vector field and if I fix also the contact structure, then the contact form is uniquely determined. Okay, so these are this thing. And what are the interesting examples for us? One, we said it's the sphere, the unit sphere in Cn. And here we take as alpha, I'll call it alpha naught, is the restriction of something which I will call lambda naught to the sphere, where this lambda naught is the say a radial primitive of omega 0. So 1/2 pj dqj minus qj dpj. Okay, if you restrict this one form here, you take a contact form, and the Reb vector field is precisely the generator of the Hopf vibration we talked about before. Okay, and more generally, if K now is a star-shaped set, star-shaped, actually the precise condition is, so K is it's a neighborhood of the origin, and what we need is that the boundary is transverse to the radial direction. So here is the origin somewhere. We want the boundary to be transverse to this. Then you can play the same trick. We call alpha k the restriction of lambda 0 to the boundary of k. And this is it's a contact form, and the Reb flow, the integral lines of the Reb flow, are precisely the characteristic lines we talked about before. And the period now, this is a good flow in the sense that the period now agrees with the action. So the systole of our set, we said it's a closed characteristic with minimal action. It's the same as saying I take the Reb flow here and I take the minimal period of a periodic orbit. Okay, these are this thing. And the next observation is that when K, so K is star shaped, so I can always represent it as this way. It's R times U, where U is on the unit sphere. And R is a positive number, which is governed by, goes from 0 to some function f of U. So I have a function f on the sphere with positive values, let's say smooth. Okay, which is the function which tells me how far I go. Okay, my K, I can represent it in this way. And then the observation is that if I take the radial projection from the sphere to the boundary of K, okay, I just project along rays, and I do the pullback of alpha K. So here I had this contact form. Here I pull it back to the sphere. What you get, you do a small computation. This is actually this function squared times alpha 0, the same one we had here. So in other words, what we are saying is that there is a one-to-one correspondence between these star-shaped sets and contact forms on the sphere. Okay, to every star-shaped set, I associate a contact form on the sphere with the usual contact structure, and the other way around. They're really the same thing. So instead of modifying sets, for us, it will be much more convenient to modify forms, because these are more, well, the vector structure, it's something you can do better. Okay, and the last ingredient one needs is to understand also symplectomorphism. And here the result is, so well, it's again an observation. If I have a map between the boundary of two star-shaped sets like this one, K and K prime, it's a diffeo, and it preserves. So it pulls back alpha K primes to alpha K. Okay, if I have a diffeo which intertwines these two contact forms, then if you extend it just linearly, if you just do the one homogeneous linearly, the one homogeneous extension, phi tilde, will be a symplectomorphism, to be precise, between K minus the origin and K prime minus the origin. It's now a symplectomorphism. Okay, this phi tilde is just phi to the one homogeneous extension of the thing. Okay, there is this problem with the origin in dimension 4. We know how to smoothen symplectomorphism which have one singular point. So here it's a point just where we lose. So we have continuity, but we don't have too much differentiability. In higher dimension, we don't know how to do this. But for this embedding problem, since we have space, this problem that we have at the origin, we can just push it away somewhere else so that it will not bother. Okay, so this is the general framework. So in some sense, by these observations, one reduces the problem to a problem about modifying now contact forms. And I'll finish my talk just by stating one theorem, which is the theorem which then implies the other theorem which is still there. Okay, so this is the theorem which we actually, the theorem we proved, and it's actually a corollary. So same authors, So the theorem stays. Now we are on we have alpha naught is a contact form on M. M is now arbitrary. It will be, of course, in the application a sphere, which is Zoll, meaning that, say, all Reb orbits closed and same period. Okay, like exactly the one that we have on the boundary of the sphere. And then we want to perturb. The result says that if alpha now is another contact form, is C3 close to alpha naught, then there exists a diffeo phi, a diffeo of M, which brings such that phi star of alpha. So we can bring alpha in the following form. There is a function, so it's a function times alpha naught, and this function has this form. It's a product of two functions, a function t and another function which for some reason I like to think in exponential form, is e to the h, where so t is invariant. No? Alpha naught, we said the Reb flow of alpha naught is periodic, so it generates an S1 action, and the function t is S1 invariant. So it's a function on M, and it's S1 invariant. Okay, so if we had only this, we'd be very happy, we'd be very symmetric. It would be like if a domain is really invariant with respect to the S1 action in Cn. But then we have this extra term of messing things around. And the good thing is that H vanishes on the critical set of T, and also dH, so this is 0. Also dH vanishes on the critical set of T. So in some sense, at least on the critical set of T, this is lower order. And so this means that, so the critical set of T is S1 invariant. And there, the whole product now, these are also critical points for the product, okay? But therefore, since this is a critical point of this function, if you look at the definition of a Reb vector field, the Reb vector field of this is parallel to the Reb vector field of alpha 0 there. Because the differential of this form is parallel to the differential of alpha naught along there. So it means that these orbits, the standard orbits of alpha naught, are also common orbits of this. And more precisely, what we can say is that the critical set of T, so crit T, I called it, this is precisely phi 2 minus 1 of the set of short closed orbits of the Reb vector field R alpha. No, because so we had a vector field, all of whose orbits were closed same period. When you perturb it a bit, what happens? You will create a bunch of closed orbits whose period is very close to the common period. And those are one which I call short closed orbits. And then, of course, you could create also other orbits which very, very large period is. I don't see it. Okay, so in that sense, this means that this function T serves as a variational principle for detecting short periodic orbits. For instance, from this, you deduce immediately that on the sphere, you must have at least n of these closed orbits, because this T is a function, S1 periodic, S1 invariant function on the sphere, so it goes down to Cpn, and there it must have at least n critical points. But what is interesting for us is the last thing. So the minimum of this T times e to the h is the same as minimum of h, of minimum of t, sorry, and the same for the maximum, actually. Okay, so just to conclude, this is the theorem, yeah, which we proved. It's a normal form for contact form close to this special Zoll contact forms. The proof involves some, yeah, old ideas of from the 70s of Weinstein, Moser, in particular Bottkol, plus something else. And this, if you translate these results about forms in the language of sets by what is written in the above Blackboard, you get exactly this, where the crucial thing is, no, you take your set, it will correspond close to the ball, it will correspond to a contact form close to alpha naught. You put it in this form, but now this function, you look at the minimal set of t, and since the minimum of t to the h is also the minimal set of t, you will find this systole there, but you will be able to embed a ball whose radius is given exactly by the minimum of t, and this gives you the relationship with the Gromov width. Okay, I think already went a couple of minutes of our time, so thank you very much for your attention.
Questions? Comments? Just wait here.
Yeah. So can you say anything about how t depends on the alpha?
So here everything is a bit, so t, I don't know, if alpha is C3 close to alpha naught, t will be, I think, don't lose much. I think it's already C2 close to the constant function 1. So t, you don't lose much. In h, you lose a bit more. You can, yeah, here you can be crazy and really quantify everything about how things depend on the other ones. The thing is, yeah, t will depend nicely on alpha. H, you lose one more derivative. Yeah.
For like infinite convex sets, or just for balls, really?
So yeah, the method, yes.
Yeah. So in some sense, you could try to perturb other sets. So the thing, you know, we want to, let's say we need to have a set for which we know how things go, and then hopefully you can also perturb those. The next step after having done the ball would be to look at ellipsoids. And there are in low dimension 4, there are results. Well, we have some results together with Marco Mazzucchelli and Christian Lange, who's in front of you, and but about not about coincidence of all capacities, just about the Viterbo, or the yeah, something similar to the Viterbo conjecture in that case. So for the Viterbo conjecture, in some sense, it's interesting to perturb the ball, because the ball is the maximizer. If I start far away from the ball, okay, I'm already, the inequality is already satisfied strictly. So if I perturb, there's not much to prove. But instead, coincidence of all capacities still is an interesting question. But with these methods, we need to start from some sets we know well, and then by normal forms push it a bit farther. Yeah.
Can you actually calculate explicitly the symplectic capacity of some set,
or?
So there is a wonderful algorithm for computing it for polytopes in R4. For polytopes in R4, it's a combinatorial. This is due to Chaim Kislev, and she found it's a very neat combinatorial formula. It's based on Clark duality, and so convex polytopes in R4. You give me, no, not me. You give maybe Chaim Kislev the coordinates of all the vertices, and she has a program where it's quadratic minimization, but it's finite thing, and spits out what is the symplectic capacity.
And even in low dimensions, can you expect the symplectic capacity for convex sets to be like a complete symplectic invariant, or that's impossible? No. Yeah, because, well, of course, with one capacity you don't do much. The thing is that there are more symplectic capacities. There's a whole sequence of symplectic capacities, and this question has actually been investigated by Ziltener, but I think all his results are in the negative direction. One does not expect that with just these capacities you can get a complete set of invariants. Yeah.
So you mentioned the resolution of Mahler's conjecture in dimension 3 by Shibata.
Yeah.
What's special about 3 dimensions? Does he use like Gauss-Bonnet or?
No, he uses, I read the proof years ago. He used a very indirect, so the proof in some sense is completely elementary, but it's based, would have to look it back, but let's say he deduces Mahler conjecture from another inequality, which unfortunately this inequality clearly holds only in dimension 3. Let's say, so it's so there is apparently there is no hope to extend this Irie-Shibata method to higher dimension. And the other thing with what makes dimension 3 much simpler is that there are just two conjectural minimizer, because there is just the cube and its polar set, which is the octaedron. What goes wrong in higher dimension combinatorically is that you have more and more. For instance, you can take an octaedron cross an interval. This is another conjectural minimizer, or you can take the 4-dimensional cube, or you can take the polar of a octaedron cross an interval. And so the set of minimizers explodes, and then to prove that they're really minimizers becomes more difficult. Yeah, I think in some sense the Irie-Shibata proof also somehow works, because the minimizers are just, there's one minimizer and its polar set and nothing more.
Thanks.
Okay, I think we thank Alberto again.
Thanks a lot. And I cannot start by saying thank the organizer for the invitation. Thank the other organizers for the invitation and the opportunity to talk here. It is a real pleasure. So I'm going to talk about a project, joint work with Viviane Baladi. This is some thermodynamic estimate for the essential spectrum of the transfer operator for a class of piecewise expanding maps in any dimension. So before getting into before stating the results and all, let me just recall you the motivation and what are the tools that we are used. Maybe most of you already knows about transfer operator. I'm sure that everybody knows why it is important sometimes in dynamical system to study the spectral property of these operators, but maybe not all of you are work with this tool every day. So the statistical properties of a dynamical systems, say given by a map. I will talk about maps, but of course you can use it also to study flows. Are related. You can get statistical properties of a dynamical system studying the spectral properties of the associated transfer operators, which I will call L, and T will denote the map, and G will denote the weight of the transfer operator. Let me recall what is the definition of the transfer operator. Imagine that you have that T is a local diffeomorphism, then and G. So T, in general, let's say that is a CR local diffeomorphism on a smooth compact Riemannian manifold M, and G is a function from M to C. Then the transfer operator is defined on function in L1, given by the sum over the preimages of the map of phi y, phi times G of y. So this is the weight, and if you take, for example, G to be the inverse of the Jacobian of the map, then the spectral properties, the study of the spectral properties of L with this weight will lead to the analysis of the SRB measures, also called the physical measures in some situation they could do coincide SRB measures. Or, for example, if you take G equal to 1, you are looking for the measure of maximal entropy. These are the two most important invariant measures of the system, and in particular, in this case, this formula is given just by the change of variables in the integral, and then using the Jacobian, you will see that the eigenvalues associated to the eigenvectors of modulus of 1 of the transfer operator coincide with the density of the invariant measures of the system. So in the nice case, I will talk about expanding maps. Let me recall you what is the situation in the expanding case. In the smooth and compact situation. So in this case, M is compact and T is smooth. Then what is important to say about the transfer operator is to have a spectral gap, or saying that it's quasi-compact. So you will have the spectrum picture like that in the complex plane, and you have here, this is the spectral radius of L in some Banach space, because if you look at the spectrum of L in L1, you will get the whole disk, which is not really useful as information for the statistical properties. So the point is to find a Banach space in which you have this sort of spectral gap, or sort of matrix situation, in which you have the spectral radius, and then you have a smaller disk. I will call this essential spectral radius of L in some Banach space B, except in this smaller disk you will have discrete eigenvalues. And these eigenvalues are isolated eigenvalues with the finite multiplicity, and they cannot accumulate. So this, the best situation. The best situation would be to prove that in the case, for example, of SRB, you can prove that the spectral radius here is 1, and you want that the essential spectrum is strictly smaller than 1. In general, the good point is to prove that the essential spectral radius is strictly smaller than the spectral radius. This gives you quasi-compactness. For example, in the compact case, you will have that the essential spectrum is 0, and you have just discrete eigenvalues. Okay, so in the smooth expanding map case by Ruel, we have this nice situation in which let me see. Okay, in which you have that L acts on the C alpha function on M. Well, when alpha is in 0 R is the differentiability of the map. And you will have that LTG is quasi-compact. So let me just write the bound. The essential spectrum here is bounded by lambda. So the expanding map case is when you have that the derivative in each point of the map is greater than some lambda, which is greater than 1. G is also CR, yes. Yeah, in that case, G is also CR. Okay, so the bound in this case is given by lambda to the minus alpha times the exponential of the topological pressure of the potential log of G. Let me write what is, in this case, the topological pressure. And this is strictly smaller, and this is smaller or equal than, and this is strictly smaller than E to the P top log of G, because lambda is greater than 1, and this is exactly the spectral radius of L in C alpha. And the topological pressure, I will write it here in its, so if you have a potential phi here, this is defined as you have the Kolmogorov entropy of the map T plus the integral of phi in the mu on M. And then you take the sup over all the ergodic measure for the map. This is actually a variational principle formulation of the topological pressure, but in this smooth compact case, this comes from the variational principle using the classical Bowen topological pressure. So you define that the pressure using span or separated set, and then you prove that in the smooth and compact case you have a variational principle for multiplicative sequences. Yeah. G, right. So this is G, sorry. I will put myself in the situation in which G is, thank you, is positive. Okay, so later on, I think in 2003, Gundlach, Latushkin gives an optimal formulation of the essential spectral radius in the smooth expanding case situation. So this is Gundlach, Latushkin. And they prove that actually the essential spectral radius in C alpha is actually equal to the exponential of, here you have the part coming from the topological pressure, and you have log G and in the mu. And then here you have minus alpha times, this is lambda, call it lambda minus dt. And this is the smallest Lyapunov exponent of the cocycle dt. So this is an optimal, let's say an optimal bound, but is an exact formula for the essential spectrum. And this is the best case in which we have smoothness of the map. The sup, yes. Thank you. Okay, so this is the situation in the smooth case, and we would like to say something in the non-smooth case, so including discontinuities, which is still an interesting situation. You can think about billiards. In that case, is not a piecewise expanding map, but the map related to the Poincaré section is a hyperbolic map. And in that case, you also have the problem that the derivative can be unbounded. But still, understanding deeply the piecewise expanding case is still an interesting point, and maybe one can extend the tools and the results in the hyperbolic case, and then think about something more complicated. So how could we extend this sort of picture in the piecewise expanding case? There are many results also in that direction. Note that it is important to have that the essential spectrum is as small as possible. So this depends strongly on the Banach space that you're using, as you will, of course, hear from many other talks later from people here at the conference. For example, in this smooth case, if you take the smoothness of the map as big as you want, you can shrink the essential spectrum here, and you will converge to a compact operator. So this would give you some nice whole description of decay of correlations and resonances. So it is important to have somehow a good bound for the essential spectral radius. And let me so now give you the definition of the map that we studied. In the discontinuous case. I will give you a general definition, and then I will make some example. So, piecewise expanding maps. Infinite dimension. So in our work, the definition of the map were some t from C1 plus alpha m. Let me just simplify the notation. Is piecewise C is C1 plus alpha m piecewise expanding if alpha here is bigger than 0. So we have a partition of the space. So there exists a finite partition of the space. So this I here has a finite cardinality, such that it covers almost all M with respect to the bag. Then the boundary of this partition, so the boundary of each set OI is a finite union of C1 compact hypersurfaces then it is natural to ask that T has an extension to the closure of each OI, such that we can have a diffeomorphism. So let's say that there exists an open set which includes the closure of each of these OI, such that and some T tilde from OI tilde to OI, which is a C1 plus alpha diffeo. And it coincides with TI with T in each OI. So we can basically extend, this is natural, extend the dynamics there. And finally, we need T to be expanding. So we take the derivative of this of the extension and apply to some vector in a tangent space. So for each vector, so we take the inf over the vector in the tangent space. Let me call it calligraphic T in M. And then we take also the inf over I in I. Maybe before that, the X in I, and then the inf I in I. So this is just the more general situation of the an expanding map, and this is called lambda, which is greater than 1. Okay, this is expanding. This is very general, but you can think about an example. Simple example could be a generalization of the beta transformation in the interval. So you can think about a map T which goes from the torus TD to TD and is given by Tx equal Bx mod Zt, and B has eigenvalues, all the eigenvalues with positive absolute value. So you have an expanding matrix here. This is a piecewise affine map case. It is a generalization of the well-known beta transformation in the interval. This fits in this setting, and there are many results about piecewise affine maps, basically from Keller-Buzy. For sure, I will forget someone about this, but let me go back on my notations in order to introduce the results. Okay, so I need also this I will recall it later. Okay, so what is the problem of studying piecewise expanding map in higher dimension? The problem is that you can have some issue due to the discontinuities and due to accumulation of discontinuities, often called entropy multiplicity or complexity, depends on the literature. But basically, and let me define it here. So the higher dimension situation gives you complexity defined as here. So let me take some positive integer n, and let me define the cylinder set as always. So you have some word here in I to the n. And the cylinder is defined as I take some element of the partition indexed by ik. I take the preimage by k, and then I take the intersection from 0 to n minus 1. This is standard. So the complexity is given by, I want to measure, to count the cylinder that can intersect in a single point. This is what gives you the complexity, and that can create some problem. So it is a sequence which depends on t, but it depends also on the partition of the partition O, and is given by so basically I take the I such that OI contains some point x in some point x in M, and then I take the cardinality of this set, and I take the maximum over dx. So I'm counting how many cylinders intersect in a single point x. Okay. So, for example, in one dimension, you don't have so the problem comes when you want to when you iterate the map and you want to control the growth of this complexity. That in the smooth case is not a problem. So let me define also the limit as n tends to infinity of 1 over n logarithm of dnt. Okay, so this complexity were used in order to study piecewise expanding map. Let me just give you some remark in d equal 1. You always have in d equal 1 that this guy is 2, because you can have just 2 cylinders that intersect in a point, and so this this asymptotic limit will be 0. So this in dimension 1 does not create any problem. T is equal to 0. In dimension greater than 1, you may have some problem, and because when you try to look at the bound for the essential spectrum, iterating the transfer operator, etc., you will have that this guy can grow depending on the map. And in some work in which we were inspired, Baladi, go with Zell. And there are 2 works and in which the authors studied the piecewise hyperbolic maps with some conditions. I think this is 2009 and 2010. And later on, Tomin. Yeah. For the complexity, or I was talking about general piecewise hyperbolic maps, and the essential spectral radius of transfer operator for piecewise hyperbolic maps. And to mean in the case of piecewise expanding map in 2011. Okay, in dimension one, actually now that you mentioned something, in dimension one we have an optimal bound for the essential spectrum for piecewise expanding map. Looking at the transfer operator in BV, this is a result by Keller. Don't remember the, maybe it's an old result, maybe 1984, I guess. 94. Okay, thanks. So in dimension one, we have that if we look at the essential spectrum of LTG in BV, this is given by, here we have the product for K0 to n minus 1 of GK, G composed with TK. You take the L infinity norm of this guy to the 1 over n, and then you take the limit as n tends to infinity. Okay, this is a result by Keller. So in dimension one, we have an optimal result. In dimension greater than one, we have these results use, they have a conditional formula for the essential spectral radius, which depends on the complexity, but not only on the complexity. This is called in this paper's complexity at the beginning, in which you look at the cylinders containing X, but also it uses complexity at the end, in which you have the same formula, but here you have that X belongs to the image of the cylinder I by the map Tn. So in that case, so let me call it here dB, 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 dn, t. So here you have the same thing, but you have Tn OI next. This is called the complexity at the end. Differently from the complexity at the beginning, in which for dimension two, the good news is that dBt is equal 0 generically, and this is a result of Corison in 2000, I guess. This is the best that you can hope, because there are some examples by Zuji and Busey in which they construct some piecewise expanding maps that they do not have this, for which this is not true, and they can show that these systems has no, for example, they do not have even an SRB measure. But Corison proved that the complexity dB is 0 generically in dimension greater than 2, and in the for general piecewise expanding maps, but DENT can grow exponentially. For example, if you compute the this term in the case 2x mod 1 in 0, 1, you will have that this guy grows as 2 to the power n. And this is a problem, because you need to, you will have that this is greater than 1, and you cannot hope to have a control on the essential spectrum, because what we want to prove is to have a smaller essential spectrum with respect to the spectral radius of the transfer operator. That, for example, in the SRB case is 1. So you want something that is strictly smaller than 1. So you have, if this guy is involved in the computation, you will have that this grows exponentially fast, and it can ruin the estimates. So in these papers, this is the complexity at the beginning. Okay, in this. Yeah, but this is DE. Yes. Also, DB also in this case trivially is 0. Yes. Okay. Yeah. This is all the point. The problem is that in these results they have a formula for the bound of the essential spectral radius, but it involves also these complexity terms that they can kill, taking appropriately scaling appropriately the space. But I will get into the details in a moment after stating the results. Mostly, we would like to have a sort of yeah, it's there. 2. Yeah. Yes, I didn't write the formula. I will write the formula. It will be more clear. Yes. General relation, it should be, yes, with the exponential of the topological entropy. So results. Let me check here. So in our results, the Banach spaces are the classical Sobolev spaces. Then I will denote by HTP. Then are the spaces used also in Tomin paper. And I won't give you the definition. This is just, you have T weak derivative in LP in M. And the main point is that the parameters satisfy this relation. T is smaller than 1 over P. In particular, is smaller than the minimum between alpha and 1 over P. And P is greater than 1. So, this condition that T is smaller than 1 over P is the main condition that we use in order to deal with the characteristic functions by some old result due to Strichards. And the first result is a formula for the bound of the essential spectral radius. So let me call this, since I already written here, I will call it GN for simplicity. So we looked at the essential spectral radius of LTG in this space HTP. And this is bounded by the exponential of, this is the complexity at the beginning, this guy here, times 1 over P, plus this, And I forgot to tell you who is the pressure. I will write it and then tell you. So this is a sort of topological pressure for a set M and a sequence P. This is the inverse of the minimal expansion. So this is the sequence. Now I will write you who is and T. I want the pressure depends on T, of course. Okay. What is this pressure terms? So sorry, I forgot. Yes. The assumption of G, yes. So G is piecewise older. I mean that is piecewise older with respect to the partition. Alpha older. Where alpha, yes. Alpha is right. You remember that the map is C1 plus alpha, and the weight is piecewise alpha older. And the complicated formula is the pressure of a subset. So let Fn, this sequence of functions, which are submultiplicative with respect to the map T. This means that Fm plus n computed on X is smaller or equal than Fm computed on Tn of X times Fn of X. And let us take a subset of M. Then we can define the topological pressure called P star top of the subset E and the sequence of function Fn as the lim n tends to infinity 1 over n logarithm of the sum. Here I sum on the cylinder set, and I take all the cylinders which intersect with the closure of E. And here I have the sup over I of Fn. So it's basically a similar formulation as the usual entropy, but now this was defined by Busey and Sarig and Busey previously when they study piecewise expanding map, and the pressure in that article, the sequences were multiplicative, not submultiplicative. So we use this definition of the pressure to bound our essential spectral radius, and this depends on the subset that we choose. And the reason why we wanted to define also this pressure depending on the subset is for this paper of Busey and Sarig, that they prove that if you have a multiplicative sequence of weight here, and you look at, let me write it here. Here I can write also the discontinuity set. So the boundary is the union of the boundary OI, and the discontinuity set is just the union of the pre-images of the boundaries. Okay. So if you take a multiplicative sequence here, Bussy and Sarig proved that you have a variational principle, meaning that you can relate this formulation of the pressure with the variational principle formulation, as long as the pressure of the boundary is smaller than the pressure on the whole manifold. So under the assumption that P star top of S and Fn is smaller than the P star top of M, then you have variational principle. No, yes, here is D. Oh, yes, this is just the boundary. Thank you. Okay, so based on these results, we wanted to relate the essential spectrum bound that we have here with a variational principle as the one that I wrote. Yes? Lambda n is the inverse of the minimal expansion, but is a function of x. So is lambda n, let's say like this. Let's write it like this. Then you have 1 over the inf u. So is the function that I defined later before, but the inverse, because but it's still a function of x. Oops. Thanks. An exponential where? No, that's yeah. Well, here there is the exponential. So then you use the topological pressure. Yeah. Yes, it's yes, it depends on yeah, I guess it depends on how do you formulate the weight. If you take the weight like in the multiplicative case is the same. Yeah. So let me cancel this. How much time? Okay. I will speed up. Mm-hmm. Let me see. Yes, I guess we put a log. Yeah. The soup of, yeah. Yeah. So here. Sorry, yes. Oh, yeah. Yeah. Thanks. Yes. Any other logs? Okay. Okay, so that was the first. Let me just give you a remark. So if you take t equal 1, I told you that dbt is equal 0. So this guy becomes 0. And you have that you can easily bound this by e to the p minus 1 over p. So you take out the supremum, the lim sup of the function. So you are left with the topological pressure of 0. And meaning that you take log of 1. And then here you have the limit as n tends to infinity of what is left is gn and then you have the derivative t prime to the 1 over p minus t. Then you take the norm L infinity of this guy to the 1 over n. So if you take dimension 1 and you take p tends to 1, when p tends to 1, t tends to 1. So you take p tends to 1 and t tends to 1. This guy is 1, and this guy is 1. And so you recover the Keller bound in one dimension. Okay, because I'm saying that H11 is BV. Just a remark in one dimension. And the last result, well, there are two results, but let me go fast on this. So we use this argument of Bussy and Sarig here for submultiplicative potentials, and in the piecewise expanding case, and the submultiplicative potential to prove a variational principle of that kind. So if you take if p star top of m and the log, so here we take any piecewise alpha order continuous submultiplicative sequence times nu and t, and the nu n is the same there. And we compute the pressure at the boundary. So under the condition that the pressure at the boundary is smaller than the pressure in the hole, same thing. Then we have a variational principle. So we have that p star top of m with this sequence here. Is equal to the sup over mu t of the formula that I wrote before. Integral of log g minus t lambda mu t minus. I hope I didn't forget anything. So we have a variational principle also in this situation. G depends. No. This is for general G. Yeah. This is for general G, but you put the multiplication with this that gives you the Lyapunov exponent. That is the point. And then we apply this result with G being that function over there, which depends on P, right? So when you apply this result there, you will have that you will have that. Let me just write it, and then I will stop. So now this guy still there over P. And then I have all this soup here. T. This is P over P minus 1 plus log of G and the Jacobian to the 1P and the mu. And then I have the Lyapunov exponent. Okay. So this is the last result under the small boundary pressure condition. And as you can see, if we take P tends to, let's imagine that we have that our map is smooth instead of piecewise smooth. If you take P tends to infinity here, this guy goes to 0, this guy goes to 1, and this guy goes to 1. So you recover the Gunlach-Latushkin result for the smooth case. If you take P tends to infinity, and so you are looking at HT infinity, which is basically CT, the smooth functions case. It is time? No, I won't have the time to give you an intuition of the proof, but actually it's not really too much far away from the computation, because this formula over there is given by a Lasota-York inequality in HTP. And you do the computation as always, like looking at the transfer operator as the composition with the with a contraction times a weight. So when you, this is basically the transfer operator, the local transfer operator, then you sum up over the pre-images. And then you compute the LP norm of this guy, the LP norm of this guy. And this is just the change of variables. You will have the soup of the weight in a small neighborhood in which you have it. And then you will have the change of variable, the TF to the 1 over P times phi LP. This is a trivial inequality. These guys where the determinant comes out, because F here is the contraction. So it's the inverse of the map. And then you have here minus. And then you have the determinant to 1 over P. When you do the derivative, you do the same. And then you're taking the derivative in LP. And you will have a compact part that comes out from the computation. The main problem is that the transfer operator is not just the sum over the pre-images of the weight. So you will have the weight and the function, but then you will need to consider a characteristic function composed with a map, with the inverse map. This is basically a rough formulation of the transfer operator. So you have this problem that you have the characteristic function here. So you need to deal with that. And we did it as in Baladi, Guzel, and Tomin, using the fact that T is smaller than 1 over P. This assumption gives you that the characteristic functions are bounded multipliers in the sublet spaces. So the characteristic functions are invariant if you compute the norm of phi times the characteristic function of a nice set, in the 3 charts, all the results of these sets were half spaces. Then this is bounded by a constant times phi in the HTP norm. Of course, it's much more complicated than this because you need to be sure that you're looking at the space at the right scales in order to apply all of this. And then you need to sum up all the inequality again to obtain the results. But basically, this is where we use the fact that this condition gives us the control how to deal with the characteristic functions. And then we use this other variational principle in order to relate the topological pressure in terms of the subset to the variational principle formulation. And this is all I wanted to say. Thanks a lot.
Yes, thank you very much also for the invitation. It's a great pleasure to be here. And yeah, so the talk will be about 2 classical dynamical systems, namely the geodesic flow and the billiard flow and the relation between both. And there will also be some metric geometry involved. And yeah, I will work mostly in the following setting. I have some convex body inside Rn. And then, you can look at the geodesic flow on the boundary of this convex body. And by geodesic, I mean a curve on the boundary which locally minimizes the distance between points. And on the other hand, you have the billiard flow inside the convex body. And now you can ask, when are these 2 flows well defined? So 2 questions. And secondly, what is the relation between the 2 flows? So for instance, concerning the geodesic flow, if you have a general convex body, then it may happen that a geodesic terminates at a point and cannot be extended as a geodesic. For instance, if your convex body has some corners and you run inside this corner, then it's not possible to extend it as a geodesic because you can always find a shortcut around the corner. So, but nevertheless, there's a result by Kapovic, Petronin, and Lütschak, which says that the geodesic flow exists almost everywhere for all times, and it also preserves there's some natural Liouville measure which can still be defined. Yeah, if your boundary is smooth in the sense that CK, let's say, then you can show that the geodesic satisfies the geodesic equation, and which depend on the coefficients of this equation depend on the second derivatives of the boundary. So if your submanifold here is CK, then the flow will be CK minus 2 in general. But there are some results by Hartmann which say that if you're in R3, the geodesic flow is actually better, namely CK minus 1. Yeah, and about the billiard flow. So again, if you have a general convex body like this, then the billiard flow may not be well defined if you run in a corner, because then there's no unique way to extend it. Yeah, but yeah, even if there are unique tangent planes, it may happen that there are some strange phenomena, and this I want to illustrate by the following example due to Halpan. from 77, and which he called a strange billiard table. And again, so it's a two-dimensional convex body inside R2. And it has the property that there exists some billiard trajectory. And okay, by billiard trajectory, I mean trajectory in the classical sense, where the angle of incidence equals the angle of reflection. And so in this Halpern example, there exists a billiard trajectory which exhibits infinitely many bounce points, reflections in finite time. So there will be a accumulation point of bounce points. Yeah, and the example is such that the boundary is 3 times differentiable. And positively curved everywhere. Yeah, how did he construct this example? What he did was he started actually with the trajectory and then constructed a table so that this is the trajectory of the billiard table. Namely, so if you have the trajectory, then you know how the tangent planes have to look like so that this satisfies the reflection law. And then you have to find some continuation in between to and make sure that you get this regularity. Yeah, and in the same paper, Halpern also showed that if the third derivative is actually bounded, then such a phenomenon cannot occur. Okay, and some years later, Huber showed a similar statement in arbitrary dimensions. So if you have a convex body in Rn, whose boundary is 3 times differentiable, and let's say C3, then billiard trajectories do not exhibit infinitely many accumulation bounce points in finite time. Okay, and in higher dimensions, so in this 2-dimensional example, this is simple in the sense that you only have one geodesic in the boundary. In higher dimensions, you have many, and you may also ask, well, how is the geodesic flow, or how are the geodesics related to the billiard trajectories inside? Yeah, and to answer this question, it is helpful to have a common description of billiard trajectories and geodesics. So, and one idea to describe billiard trajectories in terms of geodesics is that, so if you have some polygon in the plane and you want to describe a billiard path, then instead of looking at the billiard path, you could try to reflect the table instead and follow a straight line. Yeah, this idea can, for instance, be used to show that any polygon with rational angles has a periodic billiard trajectory. This was shown by Maser. And another instance where this idea applies is a result by Burago, Kononenko, and Verleger, where they showed that you are given n hard balls in Rn. And you prescribe some arbitrary initial velocities. Then they showed that there exists some constant, which they explicitly described, such that there are at most n of n many collisions before all the balls run in different directions. Okay, so one might try to do the same thing here, but the problem is if you take this example and you glue two copies along the boundary, then still this path cannot be extended as a geodesic in this double. Yeah, so here this result by Burago and his co-authors, this is used, this is based on methods from metric geometry, which also turn out to be helpful in this problem. And therefore, I would like to give you some introduction to this theme. So it's a comparison geometry a la Alexandrov and Husemann, for instance. And the idea is as follows. So you have a metric space, let's say a complete geodesic metric space. And yeah, by geodesic, I mean that if you have 2 points in your space, you can always find a geodesic which between these points, which realizes the distance. And now one says that this space has curvature, non-negative curvature, if the following condition is satisfied. So if you pick any geodesic in your space, call it gamma, goes from gamma A to gamma B, and you take any point P in your space, then this determines a triangle. And you can look at a triangle in R2, which has the same side lengths. So this side has the same length as this one has the same length as this one, and so on. And now the condition is that if you look at the distance from P to points on this segment, this distance should be at least as large as the distance in the corresponding space in R2. Trying, yeah, as a comparison distance. So examples. Yeah, and actually, it is actually enough to check this locally. So if you have for any point a neighborhood, such that for any segment and any point in this neighborhood, this condition is satisfied, then this holds everywhere. So examples are convex sets in Rn. And also boundaries of convex sets in Rn. So for convex sets, it's trivial. You just take the same triangle here, and you have an equality then, and here you have to work a bit. Yeah. Okay, and now it turns out, so my goal was to give a uniform description of billiard trajectories and geodesics. And for that, I will reformulate this condition a bit. So first of all, I can put squares here that doesn't change anything. Let's call this star. Now, if I subtract t squared on both sides, yeah, and I should also say I want to assume that these curves here are parameterized by arc lengths. Then I can define a function phi, which is d squared, the distance of gamma t to p minus t squared. And if I subtract t squared on this side, then I get a linear function, because the quadratic term is exactly t squared, because I parameterized this by arc lengths. So this is bounded from below by some linear function. So it looks like this. I have here my linear function and the function phi. And the linear function bounds from below. Well, what does this mean? Because I can do this for any subsegment, it says that the function phi has to be concave. Which I can alternatively characterize by saying that there are supporting directions. So the second derivative is non-positive. Okay, now I can ask, by definition, my geodesics satisfy this condition. Are there perhaps other curves which satisfy this condition? And I will give them a name. A curve parameterized by arc lengths in X is called quasi-geodesic. If let's call it gamma, if this condition is satisfied. So if for all p in X, the distance squared from gamma t to p minus t squared is concave. Okay, so this condition has the advantage that now this notion is stable under pointwise limits, because if you have convex functions or concave functions which converge pointwise, then the limit is also concave. So this is stable under pointwise limits. For instance, if you have the boundary of such a cone in R2, and you look at some geodesic, which may look like this, if this cone angle is pi, and you make this distance smaller, then in the limit, you get a curve which runs into the tip and comes back the same direction. So this will be a quasi-geodesic, but obviously not a geodesic. Yeah, and this class of curves has other nice properties, namely Petronian and Perelman. They have shown that if I give you an initial condition, then there's always a quasi-geodesic which starts in this initial direction, and they also showed that it can be extended for all times. No, there are other ways. Yeah. So the condition is that on both sides, the angle has to be smaller than pi. Okay, so now let's think about what these curves are in Rn. So, and I'm claiming that a quasi-geodesic in Rn is actually a geodesic. So how can one see this? Step one, you first show that the curve is differentiable. And so if I have my curve gamma here, let's say gamma of 0 is 0. And now I can look at this condition for some point P and for minus P. And then I get two inequalities. And if I put them together, if I add them up, I see that I get exactly a condition which says that the curve is differentiable at this point if I do this for all points P. So okay. And step two, I claim that gamma is actually a straight line. And how can one see this? Well, once you know that gamma is differentiable, you can compare it with a straight line that has the same initial direction. So let's call this gamma. And here I define a curve C. And for simplicity, we can again assume that gamma of 0 is 0. I define a curve C of t as t times gamma prime of 0. And I look at the point P, which is C of some small number, epsilon. Then, if I look now at the function phi twiddle, which is defined as the distance squared of gamma t to P minus the distance squared of ct to P, then this function has some nice properties. First of all, it is non-negative because this is a geodesic. So this is non-negative. And this behaves like a quadratic function. So this phi twiddle is also concave. And how I choose the initial direction here of C, the initial conditions, this tells me that gamma of 0 is the same as C of 0. And also the derivatives coincide at 0. But this can only happen if gamma and C are actually the same. Okay, so in Rn we don't get other curves than geodesics. So the next thing I want to look at what are quasi-geodesics inside a convex body. So let gamma be a quasi-geodesic inside K convex. And to be general, let's look at some convex set which has a corner. Then I know that inside, in the interior, the curve follows a straight line. Then something happens at the corner, and after that, it again follows a straight line. And okay, so again, I would like to exploit this condition that the second derivative of this function, comparison function phi, is non-positive. But now I cannot look at minus p because it's not inside the convex body. So, but what I can do is, so if I write out this condition here, what I get is something like the inner product of P. So again, we can assume that this is the origin here. That this inner product is bounded from above by some constant A times T plus some O of T. And I can look at this condition at T and at plus and minus T. And again, if I add them up and then take the derivative, what I get is that P comma gamma plus at 0. So the derivative of gamma in the positive direction plus or the derivative in the other direction is non-negative. And if you look at this, you realize that this is actually the reflection, the usual reflection law. And in this case, a generalized reflection law, because there's not a unique tangent plane. So you can show that this condition is equivalent to the condition that there exists some supporting hyperplane, so that the usual reflection law is satisfied with respect to this hyperplane. And if there's only one, then this gives just the usual reflection law. Yeah. And what one can also show is that if I parameterize the boundary of such a convex set by arc lengths, then it is also a quasi-geodesic. So that in the end, this gives the notion I was looking for, which describes billiard trajectories and geodesics at the same time. Okay, then I can state the following result. If I have a convex set in Rn, such that the boundary is C to 1. So it's 2 times differentiable and the second derivative is Lipschitz and positively curved. Then there exists a unique quasi-geodesic flow which is defined on the tangent cone bundle of this convex body. Yeah, so, and moreover, this flow satisfies the following condition. So first of all, if you, so it satisfies some continuity condition in the sense that if you look at the flow itself is not continuous, because if you are reflected at a phase, then you have a flip in the direction, so a discontinuity. But the composition of the flow with the base point projection this map is continuous. Yeah, and here continuity is defined in terms of, for instance, you have natural subspace topology on the tangent cone bundle, which comes from the topology on the tangent bundle of Rn. And secondly, so the second condition property which is satisfied is that if you restrict this flow to the boundary, to the tangent space of the boundary, this is the geodesic flow. In particular, this tells you that if you have a sequence of initial conditions which converge to the boundary, to some tangent vector of the boundary, then the corresponding billiard trajectories will converge locally uniformly to the corresponding geodesic of the boundary, which starts in the same direction. Yeah. Okay. Let's. Okay, then yeah. Inside, well, I just tried to explain that if you have a quasi-geodesic, which is in Rn, okay. So actually, this definition of a quasi-geodesic, you can also, it's equivalent to making this definition locally. And the same argument shows that it's enough if you have points which are close by, then it's still a geodesic. Right, and the theorem also tells you that in contrast to this Halpern example, so in the Halpern example, you have this trajectory which runs inside the boundary. And so this is a quasi-geodesic, and the boundary parameterized by arc length is also a quasi-geodesic. So here you have branching quasi-geodesics. And this does not happen if the boundary has this regularity. Also, this is not in contradiction to the Halpern example. So here the boundary was 3 times differentiable and the third derivative was bounded, but a differentiable function doesn't need to be Lipschitz continuous. Okay. Then I can state the following. So now one may ask what happens if you look at more general convex bodies, which are not necessarily have unique tangent planes. And then one can phrase the following conjecture. So if a convex, some rigidity conjecture, if a convex body admits a continuous quasi-geodesic flow, then all tangent cones so if you take any point, then you can define the tangent cone, which is the span, the closure of the span of all directions which start in this point inside the body. And the conjecture is that all tangent cones are Weil chambers. So what does this mean? Let me explain this in dimension 2. So this is true in dimension 2. And in dimension 2, being a Weil chamber, well, first of all, if you have some convex set in dimension 2, then a tangent cone at a point is just, it's uniquely defined by its opening angle. And this condition then says, so being a Weil chamber means that this angle has to be of the form pi divided by n for some integer, some natural number n. Yeah, in particular for polygons, there are only 4 possible polygons in R2 such that the billiard flow is continuous, namely rectangles, isosceles, equilateral triangles, And so triangles which I get if I cut this into two halves, and triangles of this type. Okay, and you get this list by exploiting the condition that at each vertex you have some angle of this form, special form. Okay. Yeah, in particular, the conjecture also says that if you have some smooth curve in R2, or yeah, any curve which does not look like this, and you take such a cone, then you can play billiard inside this cone. And this the induced billiard flow will, for a smooth curve, will never be continuous. So this is if the curve is called gamma. So the billiard flow is never continuous if gamma is, for instance, smooth. So, for example, for the circle, it's not continuous. Okay, then in the rest of the time, I would like to focus on the, yeah? Okay, sorry, I did this, said this in an unclear way. The conjecture is that this is never continuous, sorry. So this is part of the conjecture. Yeah, I know for many curves, so for instance, for the circle, it's not continuous, you can check. And for curves which have symmetries, reflection symmetries, you can also show it. But in general, I don't know. It's also part of the conjecture. Okay, then I want to focus now on the geodesic flow on the boundary. And I told you that, so if this is CK boundary, or more generally, CK submanifold. And if K is at least 3, then geodesics satisfy the geodesic equation, which is a second order ODE, and the right hand side of class CK minus 2. And then standard ODE theory implies that the geodesic flow is also CK minus 2. So, but then Hartmann showed that for a surface in R3, the geodesic flow is actually, so this was in the 50s actually. CK minus 1, and this even for K at least 2. But now one can show that actually this holds in any dimension. So for a CK submanifold of Rn and K at least 2, the geodesic flow is of class CK minus 1. Yeah, so the difference is that if you have a CK submanifold of Rn, then the metric is CK minus 1. Yeah, so maybe you are thinking of the Nash embedding theorem. So if so if you have a CK, so a general Riemannian manifold with CK metric, then Nash's embedding tells you that there's a CK embedding, but because the derivative are involved for the metric, the induced metric is only CK minus 1. Yeah, so then I can say something about the proofs. Yeah, so let me say something about the proof of this theorem. So the idea is, the first observation is that, so if you want to say show that something is CK minus 1, you can try to show that its derivatives are CK minus 2. And what are the derivatives of the geodesic flow? Well, if you have a geodesic, you can look at a geodesic variation. So you vary the initial condition, and this gives you one parameter family of geodesics. And then you have a variational parameter, let's call it S. And if you take the derivative with respect to S, you get a vector field, which is the so-called Jacobi vector field. And this vector field also satisfies in ODE, the so-called Jacobi ODE, which is of the following type. The second derivative is equal to the curvature so this is an ODE, which is where the right-hand side depends on the curvature, which is some intrinsic property of the manifold. And while for a general manifold, this depends on the third derivatives or on the second derivatives of the metric. For a submanifold, if you do the computation, this only depends on the first derivatives of the metric. The only problem is that in this computation, you have to interchange derivatives, which is problematic in low regularity. So for instance, in the case of C2 submanifold, then the geodesic flows are a priori only continuous. So you cannot argue like this. But in this case, you can work with approximations. So you have your manifold, your submanifold, then you can approximate it by smooth submanifolds. And for the smooth submanifolds, you have this equation. And this gives you a control of the modulus of continuity of the Jacobi fields of the approximations. And then you can show that the sequence of Jacobi fields of the approximations are actually equicontinuous, so that you have some continuous limit. Yeah. Then one may wonder what happens if if the submanifold is only C1. So for C1, so this theorem might suggest that there exists something like a continuous geodesic flow, but this is actually not the case, because if you again think of this example which I explained in the beginning, this Halpan example, what you can do with this is you take two copies and glue them, then you get a topological sphere, and the metric is C0, and then you can again use Nash embedding theorem, realize it as a submanifold, and this submanifold has actually bounded curvature, but the geodesic, it does not even have a continuous quasi-geodesic flow. So yeah, okay, I think I should stop then. If you have questions, I'm happy to answer them, of course. Thanks. Yes. Right, yeah.
Of the geodesic. What about existence for these quasi-geodesics?
Yeah, so this is a nice property that for any direction you get always a quasi-geodesic which starts in this direction.
For all time?
Yeah, for all time. This is a very difficult result by Perelman and Petroni.
Okay.
So of course, for a geodesic, you don't always have, like if you have a tangent vector here of the boundary, then there's no geodesic, but you always have a quasi-geodesic.
Okay, so existence is always the case.
Yes.
Because of this Petronian, Perelman. Okay, thanks.